Hello. In this session, we discuss the case of a rectangular loop in a magnetic field. So I consider a rectangular loop here, P, Q, R, S, P, carrying a steady current I along P, Q, R, S, P, same directions. And there exists a magnetic field in the plane of the board along this way. So a set of magnetic field lines are going like this, and they are uniform magnetic field. In that, the rectangular loop is kept like this. Now what will happen to the rectangular loop when the current flows through it? That is what we want to identify. We studied that if a straight conductor carrying current is placed in a uniform magnetic field, a force is bound to act on it. That we did. Now when you look at this problem with PQRS together as a rectangle, it will be a little bit confusing. So we will do one thing. We split this rectangle into four pieces. PQ, one part, QR, RS and SP. So you will be getting four straight conductors carrying current. That you can apply the result we already obtained. So like that, when we consider the four sides of this one as straight conductors, let us consider the first case. Here, along this direction, if you consider QR part, let me take it as this side as 1, and this is side 2, this is 1, side 1, side 2, side 3 and side 4. Okay? So if I consider the side 2, in that case, the current is flowing along this way, that is, and magnetic field is along that way. Then the force will be acting downward. See, this angle is there, not 90 degree, there is an angle theta, but still, the force acting on this one will be, according to Fleming's left hand rule, will be along this direction. Let me take it as F2. But opposite to this, there is SP coming. The side SP, the fourth side, you can see the current is just opposite to this one. Current is along this way, field is along that way, right? Then the force will be acting in the upward direction. Force will be along the upward direction. Let me take it as F. Now here the direction of flow of current and the direction of magnetic field will be having an angle theta, therefore the force F2 will be equal to I into B into sine theta, you can see. Sorry, there is one part missing. I into length of the conductor into magnetic field into sine theta, you can get it. Okay? But when it comes to this side, the angle theta is now here coming, so 180 minus theta you have to consider, and finally you will be getting that side also. F4 will be equal to I into B into B sine theta itself. So force F2 and F4 are found to be the same but acting in the opposite direction along the same line. Therefore, effect of F2 and F4 will be cancelling each other as far as the rectangular loop is considered. Now let us concentrate on side PQ. PQ, magnetic field is along this way, PQ comes vertically in the magnetic field and the current is flowing downward and there is a force acting which is field along this direction, current vertically downward and the force will be towards you. Towards you the forces. So I can draw the force towards you like this. Let's get that part we have taken it for magnetic field. So let me draw that towards you like this, F1. But at the same time, what about the side 3? Current is in the upward direction, magnetic field along this direction, same thing. But the force is into the plane of the ball. That means this side is acted upon by a force which is into the sign, say into the plane of the ball. That is F1 is towards you and F3 is into the plane. Now what will happen due to these two forces? Let us see the magnitude of F1 and F3. F1 will be equal to I into L into B into sine 90 and F3 will be equal to I into L into B into sine 90. So F1 equal to F3 equal to I L B. You are getting? But the problem is both are oppositely directed but acting from two ends of two sides of the conductor. So the case is like this. So here this side the force is towards you and this side it is towards me. What will happen is due to that force the rectangular loop starts rotating. As the forces are acting on two edges or two sides here, therefore they will be making the rectangular loop to rotate. That means the force F1 and F3 constitute a torque on the rectangular loop. So the torque that will be making the rectangular loop rotate, that torque too will be equal to, we can take that from the last year's rotational dynamics, torque is equal to either force multiplied by perpendicular distance between the forces. This is the condition for torque acting. Now to find the torque acting, we have to consider the case in another way to understand it. Length is L, breadth is B, or that we consider. Now, let me raise it off to find the torque acting. So torque acting will be force into perpendicular distance between the force. Now, if I look at the problem from top, if this is the rectangular loop, so I am looking down onto it like this. So when I look like this, I am seeing this breadth along and the two force directions I can draw. Then that case, it comes like this. This is S and this is P. I am looking from the top downward. Then there will be a force that is towards you. This is F1 and this is the force acting into the plane. As I look, it looks like this. Okay? And this will be the direction of magnetic field. So this is F1, this is F3. So between F1 and F3, if I consider P, S and X, let us say, there will be a right angle triangle coming. Then, if this is angle theta, this is also theta, and therefore, you can see the side XS, this side length will be the perpendicular distance between F3 and F1. Because F1 direction is like this, F3 is like this, and this is the perpendicular distance between the two. Therefore, this XX I can take it from this triangle, that is, from triangle PSX, Sx by Sp is equal to sin theta, opposite side, sorry, not sin theta, Sx is adjacent side, then space, therefore it is cos theta coming. Therefore Hx will be equal to Sp into cos theta. Therefore Sx will be equal to B cos theta, you get. Let it be there. Sx will be equal to B cos theta, you get. Now I can substitute into this equation. We got tau equal to ILB, force F either force, into Sx, that is perpendicular distance between the force, that is B cos theta, and therefore tau will be equal to L into B. Together I can type that L into B together I can write it as area of the rectangular loop A into B into cos theta. So there is a torque acting on the rectangular loop. The torque is given by I into A into B into cos theta. But sometimes you are getting a rectangular loop with n turns. Then, if there are n number of turns coming, then the equation will be tau will be equal to n times I into A into B into cos theta. It is. Okay. Now remember, the angle theta, in this case, it is the angle made by the plane of the loop with the direction of the magnetic field. Remember, angle made by the plane with the direction of the magnetic field. Okay? So this is the equation for torque acting. So remember, whenever we keep a rectangular loop carrying steady current in a uniform magnetic field, definitely a torque will be acting on it, and the torque is rotating the rectangular loop. This idea we can use in the making of moving coil galvanometer, that we will discuss in the next session.